how many are there? 30. Okay. All right. So let's get started. I apologize for the uh, poor recording that happened for the last class. So, and for those who could not attend because of your quiz, for the benefit of those students, I will basically do some of these, kind of review some of the material that I went through last class, and I have some additional material. So I think it will benefit everyone. Okay. All right. So the thing that we are going to see today is basically we look at yesterday, or rather the last class, I was looking at the different elements in a PDK, or rather what is called as the process design kit. And we looked at the structure of a resistor, different types of capacitors, and so on. We'll go a little deeper today. We'll look at different parameters that affect them. And before that, I just want to give you an overall picture of what exactly this entire IC design looks like. Okay, so just bear with me and okay. Yeah. All right, let me share my screen. Okay, so for those who joined a little later, Kandan, thanks for putting up the WhatsApp invite link in the chat box. All those who are crediting and auditing this course or just sitting through this course, please do join this WhatsApp group so that you will basically get the information up to date. Okay. All right. So yes. Okay. Now, this particular image basically shows, I hope you can see it. All right. Okay. Okay. So this is a typical a chip. Okay. What you would see is only a black, thing that if you look at many of the boards, if you look at PCB boards, right? Like in your analog electronics lab, you would have used these DIP packages, DIP packages, right? 555 timers, op amps. So they have these DIP packages where you have leads coming out. Now, what is shown here is what is typically called as a QFN package, okay, for high frequency circuits. And many of these circuits that you would see, especially if you take a motherboard of a mobile phone, or if you take the motherboard of a laptop or a computer, you will see that the packaging does not look like your op-amp packaging. Okay, so there are different types of packages, and different chip vendors give the same IC in different packages. Okay, now this is one of the packages, but typically if you take any chip, okay, irrespective of whatever package it comes in, okay, at least to a first order, right? What you will have is the package is much larger in size, okay, the kind of the gray area that you see here, okay, and there are different leads. Okay, this is basically a 16 pin package. You have 4 pins on each side. You have 16 pins, but the actual CMOS die is what you see inside here. Okay, so this always happens. Like a typical QFN package will be 7 mm plus 7 mm, but inside that package, the die can be as small as 1.5 mm cross 1.5 mm. Okay, and different chips will have different dimensions, so we can never say that this is the standard size. Okay, now from this is the actual CMOS die. From this to the connections or to the ports, you have what is called as bond wires. Okay, now these bond wires are typically made out of gold because of their lower resistance, and also for their mechanical properties. Okay, so this is the package. These are the pins of the package. Okay, the pins can be different for different packages, but assuming a QFN package, this is how it is. Okay, now these bond wires connect the package to the die, and on the die you have what is called as pads, IO pads. Okay, input output pads. Now these pads are the pad on the package on the die, and the pad on the package or the pin is connected through this bond wire. Okay. Now, right, let's look at this particular image. Okay. Right. So you can see this is how it is. This is one bond wire and one pad, which is kind of zoomed in. Okay. Now this particular part, okay, this metal part, insulator oxide, silicon substrate, this is all part of the die or the chip. Okay. Now you have a metal pad like this. This is IO pad, and the bonding wire or the bond wire comes and makes contact with this metal here. Okay. So this is an actual, I think maybe a TEM image or a SEM image, I'm not sure which one it is, of a bond pad, okay, on a chip. And this is the close-up SEM shot or a TEM shot of the bonding wire making contact with the bond pad. Okay. Now, yeah. So this is how this is a larger chip, as you can see. Now this is the actual IC or actual die, and this is the package. And some of the pads or some of the pins can be kept at different distances. Okay, especially when it is very critical. Sometimes for RF pins and so on, you can change the location of the pin. Okay. Now there is another package which is very common now, which is called as the ball grid array or the BGA. So where it's basically a flip chip, right? So you don't have the bond wires. You eliminate the bond wires. Rather, what you have is basically a bunch of solder balls which are on top of the die, and on the PCB you have those sockets, so that you just put it and it aligns perfectly. Okay. Now, when you are an IC designer, okay, your chip will look something like this. This is one of the chips, okay, that I was involved in designing. But so you can see that this is a 48 QFN. There are 48 input-output pads on this chip. Okay, this was packaged in a QFN 48 pin package. So each of these, there are basically 12 pins on each side. Okay, and basically each of these IO pads will get linked to will get connected to a bond pad using a bond wire. Okay. All right. So this is how basically our chip industry works. All right. Now this is another, I think, SEM image of the bond wire. Basically, scanning electron microscope they have used. You can see that this is the actual die, and these are the bond wires. Okay. All right. Now the reason that I showed you is because you need to appreciate the fact that the die and the package are two different things. And these bond wires, because it is a piece of metal wire, okay, it will have its own inductance as well as its own resistance. Okay. Now that always is modeled whenever you design a chip. Okay, at the top level, you have to make sure that these package parasitics are modeled, the bond wire resistance and the bond wire inductance and so on. Okay. So in last class we looked at different components. So we looked at what is, we saw that, typically a PDK, right? A PDK will have the following components. First of all, you'll have the MOSFETs, right? And you'll have both NMOS and PMOS. And typically what happens is, in both NMOS and PMOS, each PDK will offer some flavors, okay? By flavors, I mean you will have what is called as a high threshold voltage device. You will have a low threshold voltage device, okay, and sometimes you will have RVT, NVT, and some variations of these things, okay. Ultra low voltage device, low threshold voltage devices, and so on. So there are different types. Each PDK coming from each foundry will offer certain things and will not offer certain things. Okay. Now, why do we typically have this high threshold voltage and low threshold voltage devices? Is because a low VT device will be very fast. Okay. So if you are doing a primarily, digital ICs are the ones. If you look at the market share, mostly digital ICs are there. And when you want high speed operation, you use low VT devices. Okay. In analog, we will see that when you want to have lower drop across your transistors, okay, low VDS and so on. If you want to do a lot of stacking, you end up using low threshold voltages. Okay, this is for digital. And for analog, you will basically, if you want to do stacking, or if you want low VDS SAT, we will look at these things. Okay, you use low VT devices. On the other hand, why do you use high threshold voltage devices? It's because you want low leakage. Okay. Now, what is leakage current? Leakage current is something that you will be studying in digital VLSI, right? When you have if you talk about an inverter, right, you have a PMOS and an NMOS, right? Now, some parasitic, this is your parasitic capacitance. Let's say if this is an, the output is high and the input is low, okay? What happens? The NMOS here is not supposed to conduct, okay? The NMOS is supposed to be off. But we also know from our understanding of subthreshold conduction, there will be some basically subthreshold or conduction, or what is also called as leakage current. Okay. In digital VLSI, you will look at it as what is called as the I off or the off current. Okay. Now, when you use a low VT transistor, okay, I off is high. Okay. Whereas in a high threshold voltage transistor, the I off is low. Okay. As you go to lower sub-nanometer, submicron transistors, like 65, 28, 40, 14, and so on, this I off becomes more and more prominent. Okay, so in a digital chip, you want the threshold voltage to be a little higher. If you are willing to sacrifice speed, you are mostly concerned about, let's say, not very high speed operation. You just are looking at some, maybe some 100 megahertz operation, something like that. Okay, but what is more concerning to you is low power operation. You want to limit the leakage current, then you go for what is called as the high VT transistors. Okay. Now, the other thing that we saw was basically we also have the high voltage devices, or also called as IO MOSFETs. Okay. This is just a repeat. So basically, you might have 2.5 volt devices or 3.3 volt devices. Basically, this is to interface with the outside world. We have also resistors, and as I mentioned, there are resistors using poly, basically polycrystalline silicon. Okay, we keep using poly as the, okay. You also have diffusion resistance, okay, and you also have metal resistors. Okay. Now, when you talk about resistors, all these things, no matter which material you are using, okay, you basically have a cuboid structure, right? All right. There is a certain thickness, or let's say this is what is called as the thickness of the metal, or of whatever the resistive element. Okay, let's just call it element, right? And now this is the length, and this is basically your width. Okay, for a given process technology, okay, there will be what is called as the total resistance is given by the resistivity of this particular material multiplied by the length of the material divided by the cross sectional area. What is the cross sectional area? It is T times W. Okay. Now, this rho depends on whether it is a poly material or if it is a diffusion material, okay, or if it is a metal. Okay. Now, diffusion basically means like just the way you do your MOSFETs, right? Your drain and source region, you diffuse into the substrate, you diffuse a particular doping. Either it can be N plus doping, right? It can be N plus, or it can also be P plus, right? So you diffuse it into the thing, just like how you build a MOSFET, but basically you end up with, I mean, you do a rectangular thing, right? And you have a certain width and a certain length, and you end up with this expression for the resistance. Now, this particular ratio, because rho by T is fixed, okay, rho is given by the foundry, T is also determined by the foundry. You don't have any control over it. As a IC designer, you don't have zero control over these two things, okay. So, and therefore, these two are kind of combined into what is called as sheet resistance. Okay, this it is based nothing but rho by T, and therefore the total resistance is nothing but rho sheet resistance into L by W. Okay, this is also called as resistance per square. Okay, why is it called as per square? Let's say if I draw the top view, okay, when you do layout, you will do only the top view. You don't have access to the cross-sectional thing. You can't do anything in the cross-section. Okay, the cross-section is fixed. All you can do is only at the top view level. So let's say you're drawing a resistor which is looking like this. It has a certain length. It has a certain width. Okay. Now, what it basically means is, this is what do we mean by L by W? Basically, it is the ratio of the length to width. Another way to understand it is to say, okay, how many squares does it contain? Okay, let's assume that this is a square 1, 2, 3, 4. Okay, in whatever I have drawn here, if you assume L is equal to W, okay, you have, if you take the L by W ratio, you have so many squares. Okay, a quick way to calculate the resistance of a particular resistor in a particular layout is to basically count the number of squares. Okay, so for example, if your sheet resistance is, let's say, 100 ohm per square, okay, what is the resistance of this particular resistor? This is nothing but 100 ohm into 400 ohm is the resistance. Okay, so sheet resistance can also be viewed as the resistance per square. Okay, now even if you increase the width of it, okay, the L by W ratio will give you the number of squares you can fit into this particular structure. Okay, all right. Now this applies to any kind of thing that you have. All that changes is basically the rho. The rho of poly will be much higher. Okay, that is also called as HR, high resistance. Okay, each foundry will give you different flavors again. Okay, we will take a look at some of the things today. All right, and the other thing that we are interested in, okay, in a resistor is basically not only the sheet resistance. Of course, we are interested in it, sheet resistance. The other thing that we are interested in is basically what is the temperature coefficient. Okay, what is temperature coefficient? Basically, by how much does the resistance change per degree change in temperature? Okay, so sometimes it is measured in ppm per degree centigrade. Okay, basically what happens is, as the temperature of the chip changes, right, the value of the resistance will also change. Now, this basically is modeled as a first order coefficient and the second order coefficient. Basically, here it is, some, let's say, alpha 1 times T minus T naught plus alpha 2 times T minus T naught squared. Okay, this into the nominal resistance, let's say R naught will be your actual resistance. All right. So alpha 1 and alpha 2 will depend on what type of resistor you are using. Okay, whether you're using a metal resistor or a poly resistor or a diffusion resistor, and how these coefficients vary. Okay, that will be given by the foundry. Okay, we are not interested in finding out, what is the physical origin of these things and so on. As a circuit designer, what you need to know is the resistance is going to vary across temperature. Okay, and by temperature we do not mean the ambient temperature alone. Okay, ambient temperature.
Sir, what the unit you have written, sir? Temperature coefficient ppm per
degree centigrade. Okay, so it is measured
ppm
in is parts per million. Okay, so alpha 1 can be given, something like, ohm per degree centigrade and so on, but sometimes you rationalize it to 1 million. Okay, so so this divided by 10 power 6 will give you in terms of ppm. Okay, parts per million. Okay. So parts per million is a more a generic thing. So it applies. You can use that kind of unit for different types of quantities that you are measuring. just makes the takes care of a lot of these exponent, the 10 raised to minus 6, minus 5 numbers you will get it. So you kind of rationalize it to a million, or rather you, in this case, you might multiply by 10 power 6 and then you give that number, okay?
So how you are converting that ohm to ppm actually?
I'll show you the, I want to show you the data sheets of this one. I think it will become clear there, okay?
Okay, sir.
Yeah.
Okay.
All right. Okay. So another thing that we are concerned about is linearity. Okay. Now, all of you might say, okay, a resistor is a linear element. Why do we talk about linearity of resistors? Okay. Now, what happens is the way in which a resistor, an ideal resistor is linear. That is true. Okay. But now what happens is when you look at a real resistor, okay, if you look at something which is made of, let's say, poly or diffusion or something like that, okay, it will have some voltage dependent parameters. Okay. So now R will also depend on, okay, some kind of, let's say this is the nominal thing. Okay. It will also depend on, let's say, let me just put it as some function of the bias voltage and its bias voltage square, or some function of voltage. Okay. So basically that function of voltage will have both V squared term and V terms. Okay. So I will show you the expressions, how these things happen. I will take one PDK as an example and show you. But this is also something which we have to be a little concerned about if you are looking at very high linearity systems. Okay. Now the same thing kind of applies to capacitors. Capacitors, as I mentioned, okay, there are three capacitor topologies. One is to use a MOS capacitor. Okay, that is, we will look at it in detail a little later. There are two other structure-based capacitors, which is MOM capacitor and MIM capacitors. Okay, now MOM is basically you have a fingered structure, and MIM you have a high K dielectric. I will show you how these things are. Okay, now all these things also, okay, have what is called as a temperature dependence. Okay, so they will have some temperature coefficient. Okay, so the value of the capacitance will also have some small variation with temperature, and it will also have some variation with voltage. Okay, or rather this basically gives us a measure of linearity. All right. Now when I say temperature, it is not just the ambient temperature. Okay. Okay, now in Trivandrum, let's say it's 28 degrees Celsius, and maybe you're in another place where it's, let's say, a little hotter. That's not what we are mainly talking about. Okay, when there is current flow in the chip, okay, as the chip is functioning, okay, as current flows, there will be Joule heating, right? Because the wires and everything will have a certain resistance, right? And so there will be I squared R loss happening in those metal lines, okay, and also in your transistor, right? So this dissipates as heat. So typically what happens is there will be localized heating on the chip. Okay, so if there is a region on your chip, let's say this is going to be your die, okay, your chip. Let's say there is a lot of let's say this particular area has very high current flow. Now what happens is here the temperature will be higher. Okay, and this temperature will have some gradient in all the other directions also. Okay, so that is what is called as the thermal analysis of a chip. That is done especially when you talk about chips which consume a lot of power. Okay, there is thermal analysis also which is done. They kind of map the temperature. Even on a chip, right? Like what happens is not only in test chips but also in actual. If you look at the processors that you get, maybe some Intel, AMD, whatever processors, they also will have diodes in different locations of the chip. Okay, so now basically you measure the what you do is you feed in a fixed amount of current into the diode. Okay, and you measure the voltage of the diode, and this voltage will basically be a function of temperature, right? Basically this will tell you how hot the chip is in that particular area, And so thermal mapping of the temperature of the chip also happens. And this information is used to do thermal shutdown of chips if the heat becomes too much. Okay. Now, this heating is not a trivial thing. Okay. Typically, I mean, it depends from chip to chip. In some cases, around 15 to 20 degrees higher than ambient is what you would expect. Okay. So, for example, if the ambient temperature here is 28 degrees, you can kind of, I mean, not all chips, but typically you can say that the temperature in the chip is around, let's say, 48, 50 degrees. Okay. So that of course differs. If it's a digital heavy chip, there's a lot of switching activity, it will be higher. Sometimes it can be lower also. All right. So that temperature is what is going to affect the value of the capacitance and value of the resistance. Okay, not necessarily merely the ambient temperature. The ambient temperature also comes into picture. Okay, and if you put it inside your laptop itself will be heating up, right? So the ambient temperature there is different from what you would see in the room outside. Right? So the actual temperature near the MOSFETs will be fairly high, even if your ambient temperature is low. Okay, all right. So now with this background, I just want to go through some of the things. So in the last class, okay, where did this go? Right, okay. So in the last class, what I had done was I kind of drew the cross section or the stack up, what is called as the stack up of in a typical CMOS process. Now, all the documents that I am going to show you today are taken from the foundry called as UMC, okay, which is based out of Taiwan. And usually, many of the Indian academic institutions, not only in India, but I mean, academic institutions from all over the world, they do tape outs in both TSMC and UMC as well. Okay, and so this is a 65 nanometer process which they offer for tape outs, not only to academic institutions. This is of course a generic process which is used by so many companies. Many companies, design chips using these processes and sell them and make a lot of profit. Okay, so all right. Now this is a typical stack up. In fact, you can see that there are so many different versions. If I show you that there are different flavors offered by UMC itself for the 65 nanometer process itself. Okay, but we'll just take up this particular option. Okay. Now, if you see at the bottom, now this is the zoomed out view. Okay, it's like one big structure. All right. Right, as I mentioned, this is your substrate. This is where you start off with, right? And these are your devices, and then you have different metal layers. In this particular option, which I'm showing you, it has 8 metal layers. Okay. Now, if you zoom into the bottom, okay, this is basically your what you can call a basement, right, or your foundation. This is your substrate. Okay, this is an NMOS device. Okay, you have diffusion for your source and as well as your drain, right? Now the exact structure will be different. They will not tell you the exact structure and so on because that is proprietary and confidential. But what you can see is that there is this gate material, right? Oxide is there, and then you have the gate on top of it. All right. Now this brown thing is basically the poly contact or the gate contact contacting the gate material to the metal one. M1 is metal one. Okay. Now the source and drain diffusion areas can be contacted with this other contact. All right. Now I assume by what they mean here is for a PMOS device, what you do is the substrate typically is P minus, and therefore you can directly fabricate NMOS devices. For a PMOS device, you have to put a N well. Okay, so you diffuse an N well like this. Okay, I'm just assuming that they have done this here. Okay, so this is a P minus substrate. You put a NMOS N well here. Okay, and inside the N well you put P plus diffusions. Okay, which is not shown, but you kind of put P plus diffusions here and you construct your PMOS device. All right. Now what you can see is basically you have metal 1, metal 2, metal 3, okay, 4, 5, 6, 7 as well as 8. Okay, so have 8 metal layers, and V7, V6, V5 are all the VRs. Okay, vias are what connect two different metal layers. Okay, for example, if you want to connect from metal 4 to metal 5, you put via, not a single, usually you don't put a single via, you put multiple vias, okay, and you connect from metal 4 to metal 5, and you can run the routing. Okay. So if you take a chip, all these different metal layers will be used. Okay, now this metal layer is not there everywhere. Okay, it is present only where
Sir,
you
this
draw.
VIA is,
Yeah, sorry.
sir, this VIA is also a metal.
Yes, it is also metal.
It's another type of metal that connects to a different.
Okay, via is can be the same metal. I don't know see why there should be a different thing. Okay, it's basically a connection between two metal layers. All right, like for example, you can do a lot of routing in, let's say, metal 3. I want to connect to a signal which is running in, let's say, metal 4. Okay, so only where you want a connection, you'll put a via and then you go to metal 4. All right, it's very similar to your PCBs, right? If you have a, I don't know how many of you have designed PCBs, right? In PCBs, you have multiple layers, and then you use a via to connect between different layers. Okay, so there through-hole vias will connect all the layers together, like, and so on. But here it is a very specific via, right? Like it's a metal layer to metal layer via. Okay, all right. Now each of these metal, does it answer your question?
Yes, sir.
Yeah.
Yes, sir.
Okay. All right. Now, if you have the metal layer only when you draw it. When you have not drawn it, you will have this other bluish regions. Okay, which have different, which is basically a dielectric. Okay. So this is a more comprehensive thing. Like you can see different layer names. Okay, IMD 1A, 1B, 2A, 2B, 2C, 3A, 3B, 3C, and so on. So they have different metal. This one. So in the next page, actually, the details of that is given. Okay, so you can see that IMD 1A has got a thickness of 0.03 micron, and it has a dielectric constant of 5. Okay, so each of these layer has a certain thickness and certain dielectric constant. So this will be given. This is basically given by the foundry. We don't have any control over it. Okay. Now on top of metal 8 layer, you have what is passivation layers. Okay, and this gray one is the aluminum redistribution layer. Okay, so on top of 8 copper layers, you have what is called as a aluminum redistribution layer, and on top of it, this is what is called as a passivation opening. Okay, so when you put a pad, right, you remember the bond pad that I showed you where the bond wire is going to come and fix. You have an opening in the passivation, and that is where you make contact with the topmost metal layer, and then it comes to metal 8. Okay, and then so suppose you are taking some input signal. What happens is the bond wire will come and attach to the pad here. This is probably the pad. Okay, and that connects with a via to this metal 8. Okay, and then you can put a stack of vias and basically bring it down to metal 1, and then give it to your transistor. Okay, this is how typically connections work. Okay, now the metal layers, yeah, this is basically, this particular table will show you the thickness of each of the metal layers. Okay, so this differs from process to process, technology to technology. I'm just showing you the thing. So here if you see poly 1 is nothing but the gate layer. Okay, you have the oxide, gate oxide. On top of that, you should have some conducting material, which is basically, that's how you have the metal oxide semiconductor, right? So earlier they were using metal gates, then they moved to poly gates. So in this technology, it's poly. I think some of the more advanced process nodes are again come back to metal gates. Okay, so metal, this poly has thickness of some thickness. It has a certain range. Okay, one more thing that you need to always understand and have it at the back of your mind whenever you do chip design is nothing is perfect here. Okay, so just look at this thickness of the metal. For example, you remember the resistor thing that I just showed you, right? In the just some time back, I showed you, okay, the thickness of this particular layer. So for diffusion or poly or metal, this thickness I mentioned is not in our control. It is given by the foundry, right? Now, if you look at this thickness, it has a typical value, okay, of 0.18 micron, but it varies. It can vary from 0.153 to 0.207. Okay, everything in a chip will have a wide variation. Okay, So you can never say the thickness is this much only. Okay, you really don't know how much it is. Okay, all you know is statistically it will be somewhere between this min and max. Okay, so like that you can see for each of the metal layers, okay, you have certain thickness. You can see that for the topmost layer it is 0.36. Okay, some of the other things you have 3.25 micron and so on. So that differs from process to process. Okay, now this particular column WD min means what is the width, minimum drawn width. D stands for drawn width. Okay, WD is drawn width minimum. Okay, so in a 65 nanometer technology, the gate minimum gate width, okay, width of the gate, which actually is the length that we consider in our MOSFET calculation, is 0.06 micron. Okay, basically it is 60 nanometer. So when we say 65 nanometer technology, the minimum width or the gate length can be 60 nanometer. Okay, it can go down to 60 nanometer. Okay, and you can see for the other metal layers you have some minimum width. SD basically refers to spacing. Okay, when you lay out, you have to take care of these layout rules. Okay, you have to have at least 100 micron spacing between, let's say, metal two layers. Okay, or if you are doing in metal, you have to have at least 0.2 micron spacing. Okay, all right. Now WD is actually the physical width. Okay, basically what happens is when you draw, just like how the thickness has its own variation, right? The width will also have some variation. You can see the variation numbers here, right? So if you say I'm drawing 0.1 wide, 0.1 micron wide line, it will have a variation of plus or minus 0.01. So you don't know if it is 0.09 or whether it is 0.11. You have absolutely no control over it. Okay, in layout you will draw correctly, but then finally when the chip comes back, you can expect anywhere between 0.09 and 1.1. Okay, is this clear? This is what is called as, there is variation in the CMOS process. Okay, you never get perfect stuff here, and these variations are fairly important. Okay, so here you can see the note, metal thickness variation is plus or minus 15% for each metal layer. Okay, all right. Okay, so now let's look at the different resistors. Okay, this particular technology is offering all these different resistors. Okay, they have what is called as non-salicide P plus or N plus poly and diffusion resistor. Okay, polycrystalline. So basically, polycrystalline silicon is also doped silicon. Okay, so poly can be P plus doped or N plus doped, and diffusion, as I mentioned, is basically the actual thing which is diffused. Okay, they have another type called as HR. Okay, I'm really not sure what it is. I think they have some high resistance material. Okay, that is what that material information typically they do not give. Okay, it's all confidential. And you also have salicided, poly and diffusion resistors. Okay, now what they have done is basically they have this is document is from the foundry, and basically they have measured multiple die and they have given us the information. Okay, so this is the resistor model. Okay, although they say non-salicide poly resistor, this is typically the same resistor model for all the things. Okay, now there is some R naught, which is the nominal resistance. Here you can see it is 1 plus VCR1 times V by L. Okay, basically V by L is voltage, V is the bias voltage, L is the length. Okay, so this is the VCR1 is the linear voltage coefficient of the resistor in meter per volt. Okay, so you have a coefficient for linear voltage coefficient and the quadratic voltage coefficient. Okay, same way you have the linear temperature coefficient TCR1 into T minus T naught plus TCR2 into T minus T naught the whole square. Okay, and this R naught itself is 2 times R end. Okay, I will talk about R end slightly later. Okay, other than that you have RS times, RS is nothing but the sheet resistance. Okay, RS is sheet resistance at 25 degree in ohm per square. Okay, now this one, L is the length, width is width, with plus W is basically, delta W is basically the deviation of the designed resistor width bias. Okay, as I mentioned, as we saw earlier, there is some delta W that you can expect. Okay, So that is what. So you can see the same thing being used here. All right. Let me go to their plots. Okay. Yeah. Now this is a poly or a diffusion silicated resistor, I think, whatever it is. Okay. Now what is the end? When you say end, okay, this is the width of the thing, this is the length. Okay. At the end of it, you basically have to have contact. Okay. Whether you do it in poly or whether you do it in diffusion, you have this contacts. Okay. Typically, you may not have a single contact. As I mentioned earlier, you will have multiple contacts, and that contact is connecting to metal one layer. Okay. So in the previous expression, when you said R end, it is nothing but the resistor of these resistance of these contacts. Now, since you have three contacts, each contact will have some resistance, and you put these three in parallel, the effective resistance is what is considered. So 2 times R end plus the actual resistor is basically what you would get as the thing. Okay. Now this is some high resistance material. Let me just scroll down to okay, these are the test things. So they have verified it for all these different W/L ratios and so on. Okay. Let me see if there are, yeah. Okay. Now this is the N plus diffusion resistor, P plus diffusion resistor. You can see that the ohm per square, the median value is 102. It has a certain standard deviation. Okay. So as I mentioned, nothing is perfect. Okay. There is a variation. There will be variation in the way in which you diffuse things also. The dopant concentration and the depth of diffusion, all these things will have some variation, which will measured in terms of standard deviation. Okay. So they would have, as we saw earlier, they would have measured some 70 dies, 100 dies, whatever it is. Okay. And they would have computed the median. So you can see for diffusion resistor, the ohm per square is the lowest. Okay. Actually, metal resistors will be the lowest. They will be in the order of some single digit ohm per square. Okay. And diffusion resistors are in this range. Poly resistors are higher, and HR resistors are much higher. It's around 1K. Okay. So depending on what is the value that you want, you can pick either diffusion resistor or poly resistor or a HR resistor. For example, you want a 10 kilo ohm resistor. Okay, you will obviously go and pick a HR. Let's say you want some 20 ohm resistance, you will obviously pick up a metal resistor. Okay. If you want something like less than 1K or less than 5K, you can pick any one of these things. All right. Now VCR1, VCR2, temperature coefficient, all these things you can see. Okay. The diffusion resistor, you can see the temperature coefficient is single order one is 0, the 1 by volt squared is higher. Okay. And if you want very good linearity, you obviously go and pick up the poly resistor. Okay. The coefficient is 1.05 E minus 1 for a diffusion resistor. It is E minus 14 for poly resistor and for HR resistor. Okay. So if you want your resistor to be linear across your voltage range, you obviously pick up a poly resistor or a HR resistor. If you are okay with some variation, okay, where it is, if it's not critical, you can obviously pick up the diffusion resistance. Okay. Same thing if you look at the temperature coefficient. Okay. So here it is rationalized. So the unit here is 1 by degree C. Okay. So it is 1 by degree Celsius. Okay. And you can see it is E minus 3 here for diffusion. It's E minus 4, E minus 5 for poly. So if you want the resistance to be very stable across temperature, okay, there is one order of magnitude difference here. So you go and pick up a poly one. Okay. All right. Now this is for non-salicided. This is for salicided. You can see similar kind of behavior here. All right. Okay. Now model accuracy and so on. I think beyond this, basically they're just describing these other things. Okay. Now let's look at. Okay. I think it's time up. But for the sake of completion, let me just show you. This is the. Okay. Let's do capacitance in next class. All right. I wanted to show capacitance and other things. Okay, we'll do the other things in the next class. All right. So any doubts, questions?
Sir, what was SAB in those
Okay,
above tables?
right. Let me just show you that thing. See, they have these two different varieties. So you have a non-salicide, poly or diffusion resistor and salicided poly or diffusion. Okay. Now, SAB refers to basically the non-salicided version. Okay. Go to this particular thing. Okay. There is some SAB diffusion. SAB is for non-salicided. Okay. What it exactly stands for, what material it is, I don't know. And anyway, they have not given it also. So poly diffusion salicide resistor, HR, and this is the SAB. SAB is basically non-salicide. So probably it's a different material. That's all.
Okay, okay, sir.
Okay. So thanks everyone.
Sir?
Yeah. Someone had a question.
Sir, how is delta W calculated?
Just a minute. Okay. So delta W, as I showed here, okay, it is, see this one, for each metal layer or for poly, okay, there is some variation, okay, which is possible. And this delta W is some V table they have, width bias of each conductor, which is called wire edge enlargement table. Okay, so these are all from the, the foundry where they have, measured these things over a large number of dies and they have come up with these things. So width bias meaning like if you have something with width of 0.09 micron, okay, and you will have to, sorry, this is the spacing and this is the width, okay, and so if you have a spacing of this much and width of this much, you have to have a bias of like a delta W of this much, okay. Basically, it is like a guard thing, like you draw, so the physical width will be, that is to say, drawing width is what you do in layout. Okay, in layout, let's say you draw a 100 micron wide thing. How the foundry will interpret it is basically you'll take drawing width plus some delta W, okay, to account for these other factors, all these variation factors. That's basically how it does. So physically, if you do a scanning electron microscope image of the chip, you will see that the physical width will be drawing width plus this delta W with some variation. That is how you will see. Okay, does it make sense? So here again, you don't. Yeah. Here again, what happened? Yeah. Okay. What is your question?
Sir, so now I have a doubt that you are saying that delta W is calculated across various dies.
Yeah.
But it will vary for each die,
exactly.
right?
That is my point. Okay. That is what is called as a die-to-die variation. Okay. We will look at it in this course. Actually, yeah. So you are perfectly right. That's what this particular thing says. Okay. There is an intra-die variation and there is inter-die variation. Okay, intra-die variation means, let me share, or maybe let me take it next class. Okay, I'll be able to cover the whole thing. Okay.
Okay.
Right?
Sir.
Okay. Thanks everyone. So again, a reminder: please do join the WhatsApp group. Okay, that way it will be easier for us to disseminate information. Okay, for those of you who joined late. Okay, thanks everyone and have a nice day.